Okay, so our next this video is on power series. So to begin with, we're first going to look at this whole video is going to contain what a power series is, what's it all about, and next we'll look at the concept of convergence of power series, which essentially comes down to the interval or radius of convergence, and finally we look at how we can actually differentiate and integrate a power series. So let's continue. So a power series, as the term suggests, is basically a series that contains powers of x. Now something's completely changed here that we didn't have before. If you remember, so far we've been dealing with different types of infinite series and even infinite sequences, but we've never really seen an x present in any of the different series that we've considered. So this is the first time that, in fact, the x here that you see occurs in the form of an infinite series. So basically, as you can see here, the reason this particular expression is in fact a generalized power series. So the power series that you see here has several components. Let's identify these. So this term here, the bk, basically, this is called the coefficient. So it's called the coefficient of the power series. Okay. Right, and of course, here, this is why this is the power. So these are the various components, and there is your x, essentially. X minus c is to give us some flexibility, and this basically forms the power series. So let's look at a few terms in the power series. So if we look at the first term, we get just b0 plus b1 into x minus c plus b2 x minus c squared plus b3 x minus c cubed bn x minus c to the n. Now, of course, that's the n plus 1th term that I've shown you here. However, what I want to do is, and of course this goes on, because this is an infinite series. Here, what I want you to notice is why this is called a power series is you've got all these x terms, okay, and you've got these powers. Okay, so here also you have, say, 1 as the power. So basically this is what a power series looks like. Now this c could be anything. I mean, if it was 0, you could just have powers of x, which are just standard polynomials. But then again, you could also have the c present and it still would be polynomial. Right? It still would be a polynomial. Okay. Now, of course, what I'm going to do is I'm going to look at a particular specific type of power series, which is quite interesting to look at, where all the bk's, so all coefficients, okay, so it's a special power series, all coefficients are constant and are all constant. So basically what it's saying is your bk is just a b, all right, for the sake of argument. So for all k, okay, for all k. So that means, what that means is we end up with, for instance, example, if we let b equal 1, then what we have here is our power series changes, and for b equal to 1, you just have x minus c to the k. Okay, so now this is in the same way, or with it being b, you have k equals 0 to infinity. Okay, the b here into x minus c to the k. As long as the b doesn't change, both of these behave similarly. So what's interesting about this series? Well, let's have a look at a few terms in the series. The first term would be 1 plus this one here is equal to 1 plus x minus c plus x minus c squared plus dot 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 x minus c cubed and so on. That looks like a geometric series. Okay, so that's a geometric series with common ratio r equal to x minus c, right? And first term a equal to 1. Now this is so here we have something interesting that we could look at. What do we know about the geometric series? Well, we know that the geometric series, okay, converges to a over 1 minus r, provided that r is less than 1. Okay, so if the size of r is less than 1, we know that the geometric series converges to this sum here. Okay. So this means if we apply it to our series, this means that if x minus c is less than 1, okay, then the geometric series here that we looked at, this geometric series in the circle, okay, converges. Okay, let me write it down for you here. Okay, equals 0 to infinity. X minus ck converges to a is 1 over 1 minus x minus c. Okay, so it converges to 1 over 1 minus x minus c. So therefore, which basically can just be, we can open the bracket and it's just 1 minus x plus c. Now if I look at an example, it becomes even easier to see. So let's do an example here to the k. Now this is a geometric series clearly, okay, and here we're talking about the fact that x minus 1, the absolute value, should be less than 1. Okay, should be less than 1, which means that this implies that x minus 1 is greater than minus 1 and less than 1, which means that x is greater than 0 and less than 2. So within this range of values of x, we have our series, a geometric series, will converge. First of all, it will be convergent, and second, it will in fact converge to so for this, our series converges to 1 divided by 1 minus x plus 1. So it's equal to 1 over 2 minus x. Okay, so it converges to 1 over 2 minus x. Now, if I go back for a second, just here, just to point out that if you look at this term here, later we will be using this idea, and which is that if I were to open up this bracket, this essentially means that x minus c is greater than minus 1 and less than 1. So it means that x is greater than c minus 1 and less than c plus 1. Okay, just for your reference. Okay. Now, we've already raised an issue here, which is that there is a range of values of x for which the series is considered to be convergent. So that brings us to our next topic. So interval or radius of convergence. Now, whenever we talk about interval or radius of convergence, probably we'll end up using the term radius more, radius of convergence quite frequently. Whenever we talk about the radius of convergence, we're talking about a range of values of x for which a particular series is convergent. So you're looking at what restriction on x are there that allow or disallow a series to be convergent. So let's one thing we need to let's focus on one very important thing now. Let's move on to the power series we've looked at, which is the general power series. And I mean by that, of course, let me just remind you that I'm talking about this general power series with the coefficient bk and the presence of the c. Now, in this power series, whenever we have a power series, we will always have to find out if the series is convergent or not. We have to check that. Always we have to check. Every power series or any infinite series, our aim is always that whenever we have a power series or any infinite series, we must check it for convergence or analyze it for convergence. Now, for a power series, you can be almost rest assured that the primary tool for investigating the convergence or divergence of a power series, the main tool is the ratio test. So, as far as I'm concerned, you may not know all the other tests, but for the power series, the ratio test is usually the test to use as soon as you you have a series. Okay. Now, we want to look at what are the possibilities of convergence here. What can we possibly expect? Well, there are three possibilities. Number one, any bk x minus ck, there are exactly three possibilities. The series converges absolutely. So the series converges absolutely. All right, converges absolutely. Basically for all x belonging to minus infinity to plus infinity, which is an infinite radius of convergence. Okay, and so radius of convergence is infinite. Okay, so that's the first possibility. Second possibility is our series, any series, power series, converges only for x equals c. So converges only for x equals c. Okay, and diverges for all other values of x, and the radius of convergence is 0. And here the radius of convergence is 0. So 0 radius of convergence. So if r was the radius, here r is infinity, here r is 0. And this is only a point convergence. This is called point convergence. It is at a point. It is convergence only at a point. Okay, and the third possibility is series converges absolutely for x belonging to c minus r and c plus r. Okay, how do I get that? Well, it's not very difficult. If you remember, if r was the radius of convergence, so this occurs in the situation where we end up with x minus c, okay, less than r. So if we are in this situation, then x minus c is greater than minus r and less than r. So which means that x is greater than c minus r and less than c plus r. So this, as you can see, is what we're talking about here. So the third possibility is that the series converges for x belonging to c minus r, c plus r, and it diverges otherwise. And so I'll write it here. And diverges if x is less than c minus r or x is greater than c plus r. So it diverges if x is this greater than or, c plus r or less than, which means not in the range. Radius of convergence is r between 0 and infinity. So it's a finite number. It's a finite radius of convergence, and it's some number. It's any number. So basically, as you can see, we have three possibilities. So either the series converges absolutely for all x, which means you have an infinite radius of convergence. As here, second, it converges only for x equals c, and the radius of convergence is 0. It's a point convergence, okay? And the radius is 0. Here, the radius is infinity. The third possibility is it converges for a certain range of values, which means you have a finite radius of convergence. And if you have that situation, then the x belongs to c minus r, and c plus r between that. And here I've just shown where that comes from. Is if that happens, then you have a finite radius of convergence. So that would mean that x minus c would be less than r, some r, whatever that is. If you like, I can just show you on the side that when we are dealing with, for instance, this infinite series, quickly again, I'll just show you this is in case you're not fully convinced. Okay, so what will happen is you'll apply the ratio test here. So you're talking about limit k goes to infinity, absolute value bk plus 1 over bk, all right? And you'll have here x minus c k plus 1 over x minus c k. And this absolute value is supposed to be less than 1. Okay, so now if I just simplify this a little bit, what happens is I'm left with an x minus c. Okay, let me take it out because there's no k involved, into limit k goes to infinity bk plus 1 over bk, absolute value as well. All right, and this is all supposed to be less than 1. Okay, so what I'm going to do is the following. So x minus c, let's proceed further. X minus c is then less than 1 over limit k goes to infinity bk plus 1 over bk, right? And this, let's say that this number here is the number r. Okay, so let this be equal to r. So then I end up with this situation. Okay, so that's just to give you a guideline of how this usually happens. And once you calculate that limit, you have your r and you put that here, and therefore you get the range of values. And that's for finite radii of convergence. So here k equals, let's look at this example, 10 to the power k divided by k factorial into x minus 1 to the power k. So again, as I said, we want to prove the convergence of the series. We will do as usual. We will calculate, we will go through the ratio test, So that means the absolute value of 10k plus 1 over k plus 1 factorial. And here you have x minus 1 to the k plus 1. And this is going to be multiplied by k factorial over 10 to the k into x minus 1 to the k. Okay, that's just the reciprocal of the kth term. Now, if we notice here, this will cancel with the factorial and leave you with the k plus 1. This will all cancel with this power. This will cancel and leave you with the 10. So this is going to be equal to limit k goes to infinity, the absolute value of 10 times x minus 1, okay, over k plus 1. Now, as k goes to infinity, that is equal to 0. So that's equal to 0, and it's 0 with no condition on x. It is a 0 on no condition, for no condition on x. Okay, so So therefore, no condition on x. Okay, meaning for all x, our series is convergent. So that would be the first possibility. So the radius of convergence is infinite. So we have an infinite radius of convergence. Okay, so that's that's the first possibility. Let's look at another example where we have only, okay, here's the example. K equals 0 to infinity, k factorial into x minus 5, x minus 6, x minus 6 to the power k. So let's look at this example. Again, we go, as usual, we go through the test. So k goes to infinity, limit k plus 1 factorial into x minus 6 to the k plus 1 divided by k factorial into x minus 6 to the k. And that turns out to be limit k goes to infinity. The k factorial and the factorial cancels, this whole power cancels, and we're left with limit k plus 1 multiplied by x minus 6. Now here we have a problem. This will go to infinity except unless x is equal to 6. So it goes to infinity unless x is equal to 6. So this is called point convergence. So radius of convergence is 0 because it's only convergent for x equal. Okay, so here's the third example of the third example, and therefore the third possibility of what one can get for any power series. As we've said, you can have an infinite radius of convergence, you can have point convergence, and now we look at the third case where you have a finite radius of convergence. This is the most complicated one, and sometimes the longest also to get an answer to. So let me begin. Usually, as I said, we start with the ratio test. So let's do the k plus 1th term. There's the k plus 1th term. And then we'll multiply it by the reciprocal of the kth term. So that's quite simple, straightforward, and you should be getting used to this now. We've done several examples with this. Cancels, all of this goes away, leaves a 6 at the bottom. So we end up with limit k goes to infinity, absolute value x k over k plus 1. And don't forget the 6. So then I can separate out the x and the 6 because no k involved in that. And so I'm left with just calculating this limit. And of course, that goes to 1. So therefore, this is equal to x over 6. Now, the ratio test requires or states that if this is less than 1, okay, we have convergence. So, but the ratio test has 3 possibilities, remember. Less than 1, greater than 1, and equal to 1. Less than 1 is for convergence, greater than 1 for divergence, equal to 1, no conclusion. So we'll come to that, come to all these 3, to the other 2 in a second. Let's just finish with this one first. Well, this implies that the absolute value of x is less than 6, okay? And I'll remind you, this is the general case that I showed you with the 1 over limit. So this is what would happen. So anyway, it's x, here c is 0, so x minus whatever. So anyway, x is less than 6, which means that, which further implies that x is between minus 6 and plus 6. Okay, so that is, this is where we have convergence. Okay. convergence. Now let's move to this second case. Okay. This is the first case. This is the first case. Now, x over 6 greater than 1 implies that x is greater than 6, which further implies that we have x greater than... Okay, so we have x greater than 6 and x less than minus 6. And here we have, of course, in this region, or in this interval, we have divergence. Now, that still leaves us the situation where x over 6 equals 1, which implies that the x itself is 1, which gives us two possibilities. X equals 6 and x equals minus 6. So we don't know because the ratio test says no conclusion. So we have to test each of these two possibilities as a separate case. So let's do that next. So in order to do this, you have to in fact put them back into the original series. So the series will become, okay, the series will change by substituting in. Okay, so I'm going to do x equals 6 first. So x equals 6 means that 6 to the k over 6 to the k into k. This cancels with this, and is equal to k equals 0 to infinity 1 over k. Very quickly we notice this is harmonic series. So divergent. Therefore, for x equals 6, we have divergence. Okay? So for divergent for x equals 6. One result. And that leaves us the last one, which is we have to check for x equals minus 6 next. So that means we have equals 0, infinity, minus 6 to the k, 6 to the k, k. Now this one, a little tricky. Be a little careful here. So this will become minus 1 to the k into 6 to the k over 6 to the k into k. Again, this will cancel as before, but we end up here now with the alternating harmonic series. This is alternating harmonic series which we know conditionally convergent. So we know that to be conditionally convergent. So what we know then is that at x equals minus 6 it is conditionally convergent. So therefore our interval of convergence, the final result, interval slash radius of convergence, because that's the objective, to find that, is x is greater than or equal to minus 6 less than 6. So it's a half open interval of convergence, or we could write it this way: x belongs to minus 6 and 6. So it's a half open interval. Half open interval. Let me just do that. Sorry. Half open interval. Okay, so that's basically the third possibility and third example. So you need to be very careful in this particular situation where if it's not point convergence or it's not infinite radius of convergence, if it is a finite radius of convergence, you have to check all these possibilities. So differentiating and integrating a power series. We look at the general power series once again. So k equals 0 to infinity bk x minus c to the power k. So let's do a quick term by term of this series. So we end up with b0, as we've seen before, plus b1 into x minus c plus b2 into x minus c squared plus b3 into x minus c cubed, and so on. Now here's the situation. Now suppose we want, let this be equal to y. And if I wanted to find dy dx, which is basically the derivative of this entire series, which I can do, then I'm going to show you two ways to do this. The straightforward way, one straightforward way is to just look at this as a straightforward function which you differentiate, ignore the summation sign, and actually that should be correct. Now the other thing you could do here is, now I'm going to show you this way. If I were to differentiate this term, okay, I'm going to change the color here. So I'm going to get 0. If I differentiate this term, I'm going to get b1. If I differentiate this term, I'm going to get plus 2b2 into x minus c. If I differentiate this term, I'm going to get plus 3b3 x minus c squared, and so on and so forth, right? Now let's go back to this, this formula. Does this actually give us the same result? Well, let's have a look. Well, k equals 0 gives you nothing because of the 0, because the k here gives you nothing. So you get b0 times 0, so gone. Then you get b1, and x minus 1 minus 1 power 0, so you'll get b1, which is correct. So the next one is when k equals 2, so you get 2, there's the 2, b2, there's the b2, x minus c to the power 2 minus 1, which is 1. So that's good. Third term, b3, 3b3, x minus c squared, and so on. So the formula, as one would expect, matches whether you do term-by-term differentiation or do the differentiation of the entire thing in one go. Now, in a similar way, we can also integrate an entire series. So suppose that we wanted to get the integral k equals 0 to infinity of bk x minus c to the k dx. Then that can be written as the integral k equals 0 to infinity, bk is a constant, integral of x minus c to the k dx. That's very easily done. It's a very straightforward integral. One of the advantages of the power series is that a power series is really polynomial functions. And polynomial function, they're all polynomial functions. So as polynomial functions, one of the beauties of polynomial functions, they are continuous everywhere, they are differentiable everywhere, antiderivatives exist everywhere. So basically this will just, when we integrate it, it will become x minus c to the k plus 1. And all of this will be divided by k plus 1. And all of this, we will add just one constant, not an infinite number of constants. Remember, there's only one integration, really, of each term. And even if that, whether it could be a finite or infinite, anyway, one c is added at the end. Okay. Now I can show you term by term. Let's have a look. Let's have a look at this term by term. So we go to the original series again. I'll do it in red. So okay. So if I integrate this term by term, okay, let's do that. So the integral of so what we're talking about is the integral. So we are talking about the integral of term by term. So it's going to be the integral of b0 dx plus the integral. So I'm talking about here. If I integrate term by term, I'm going to get integral b0 dx plus integral b1 into x minus c dx plus integral b2 x minus c squared dx, and so on and so forth. So if we quickly look at this, that's going to give me b0x plus b1 x minus c squared over 2 plus b2 x minus c cubed over 3 and so on and so forth. Okay, and of course all of this will have, I'm going to put it in brackets so we know that we're talking about an infinite series, and then we have a c at the end of it. Well, we can't get to an end of it, but anyway. So now notice here that if I were to do if I were to look at some of the terms in this formula here, what do I get? Let's see. Well, k is equal to 0 gives me b0 into x minus c, okay, plus b1 into x minus c squared over 2 plus b2 x minus c cubed, okay, or is it? Yeah, over 3, and so on and so forth. Now here you might get confused a little bit and say, well, hold on a second now, wait, what is this term? There's a problem, we've made a mistake, or they're not equal. Just relax. We've seen this in integration before. Remember, this can be written as b0x, okay, minus b0c, okay, plus all these remaining terms. What is this? This is a constant. So you see this constant here, okay, and you see this constant here. All I have to do is say that one is c1 and that is c2. Essentially both are constants, and then that's all we add at the end anyway is a constant. So, okay, so these are they are actually the same. So this is how you can integrate term by term any power series.